Alright, well hello AP Physics students and welcome to this video lecture which is going to help us more fully understand rotational inertia but also help us calculate rotational inertia for various objects. Basically going through the process that we need to calculate those equations for moment of inertia, and for that we're going to be having to use some calculus, specifically some integration. But first and foremost, the most generic equation that we have for rotational inertia, we can say that rotational inertia is equal to the sum of all masses times their radius from some particular axis of rotation. Okay, so I have a couple examples here. So this is our big equation here. So I have a couple examples. In both cases we have some sort of massless rod, and at the ends we have some masses. We'll say that it's 3 kilogram masses. Okay, so in our first example here, the axis of rotation is right in the center of those two things, and then the axis of rotation for the second example here is at one of those ends, so it's at one of those masses. And what we want to do is we want to calculate what the rotational inertia is here. So let's do that. So for this first example, my rotational inertia, again, I have two objects to consider here, okay, and each has a mass of 3. So I'll start out with the red mass. The mass is 3 kilograms times the radius that it is away from that axis of rotation. So I'm going to end up with 3 times that 0.5 squared. All right, but we have to consider both masses here, okay, because the moment of inertia is the sum of both of those masses. So again, I'm going to have 3 times 0.5 squared. And if we calculate that out, then we end up getting a moment of inertia for this, for these two masses of 1.5 kilograms times meters squared. Okay, so that's our moment of inertia here for that first example. Now, for the next one, again, our axis of rotation has shifted here. So our axis of rotation is actually about one of these ends. It's actually running through one of those masses. So that actually impacts our moment of inertia, or rotational inertia, quite a bit. So if we look at the red mass, again, it still has a mass of 3 kilograms, but its radius is 0 now. So it's really doing nothing to impact the resistance that object has to change its rotational motion. And then for the blue mass, again, we have the 3 times, now the radius for the blue is actually going to be 1. Okay, so here we go. That's pretty easy calculation there. So we end up with 3 kilograms times meters squared. Okay, so these are two relatively easy examples, just basically looking at 2-point masses, okay, at some distance away from an axis of rotation. And based on the orientation that we have there, it affects that moment of inertia quite a bit. Remember, the whole key with rotational inertia is how that mass is actually distributed relative to some axis of rotation. Alright, so again, two quick, easy examples using our basic definition for rotational inertia. On the next slide, we're going to ramp up the intensity a little bit and start using some calculus to find equations for various objects. Alright, ladies and gents, so here our goal is going to be to try and determine what the rotational inertia of this thin rod is about with this axis of rotation at one of the ends. Okay, it doesn't matter which end, but for whatever reason I chose the left end. Okay, now these become a little bit trickier because this whole thing has a mass. Okay, this whole thing has a mass distributed along the entirety of the thin rod. This isn't a point mass anymore. It's not just it's not one specific amount of mass some distance away. This entire thing has mass. So there's a few things that we have to keep in mind here. First, we want to still consider moment of inertia, or rotational inertia, to be the sum of all the masses times their distance squared from the axis of rotation. But that's going to look a little bit differently for us in terms of these objects that have mass distributed along their entire shape, okay, for lack of a better term there. So what we have to do here is we have to go to this shape and we have to say, okay, I'm going to take little tiny cuts along here, okay? And those tiny cuts, they can vary, you know, they're going to vary in their distance from that axis of rotation, but these little tiny shapes are going to have some small amount of mass, and they're going to have some tiny amount of length, okay? So the tiniest little chunks, they're going to have some mass that we're going to call dm, and they're going to have some itty bitty tiny length that we're going to call dx, okay? So what this is actually going to look like now is we're going to say that all of these little tiny chunks put together, they're going to equal the moment of inertia of this rod. Okay, so notice how similar this looks. Okay, we're going to just be adding up all of those little chunks that are at some location away from that axis of rotation. So now there's one more step that we have to consider here. Again, because this entire thing has mass along its entire shape, we have to consider what we call the linear mass density of this object. All right, so the linear mass density, and you're always going to be given what this is for a particular object, but for this specific shape, this thin rod, what this linear mass density is it's just going to be the entire mass of that thing divided by its length. Okay, so this, again, this is linear mass density. So that's just telling us how that mass is distributed along the shape of this object. So again, it's just the total mass divided by the total length. Now that's a constant value, right? It's a constant value. So what this actually could look like then is we can say that it's equal to dm divided by dx. So this is really interesting now because we're saying that the entire mass divided by the entire length is constant. So that means that we can plug in our values for just this little tiny chunk that we created. That's going to be dm divided by dx. So what I want to do now is I actually want to rearrange this in term, and I want to solve for dm. So what that's going to look like then is I'm going to get dm to equal lambda dx. And so we're in a really great spot now. What we can do is we can take this expression that we have, dm is equal to lambda dx, and we can plug that in to our integration formula here, okay, for moment of inertia. So what that's going to look like then, and I'm going to do a little bit of replacing variables here. I'm going to say that the moment of inertia of this thin rod is going to be x squared lambda dx. Okay, this x squared, I just plugged x in for r. Okay, this x is still r, but it makes it a little bit clearer to see with this integration. Now, I could have called dx dr. It doesn't really matter. As long as we know that we're now integrating, with respect to x in this formula. Okay, so from here we can do our integration now, but I want us to be clear. Again, we're trying to find the moment of inertia of this rod about this end, okay, and we want to do it across the whole length. We want to add up all of these little chunks along the entire length of this rod. So my bounds here are going to be 0 to L. Now I can simplify this down. Remember, lambda is just a constant value here, so I can pull that thing out and I can say, okay, I'm going to take the integral from 0 to L of x squared with respect to x. So now doing that integration, we're going to end up with lambda times x cubed divided by 3, and then we got to remember our bounds there, 0 to L. Alright, so now plugging in our bounds, the 0 is really not going to do anything for us. So what we're going to end up here is we're going to end up with lambda times L cubed divided by 3. But now we can take this one more step and remember that lambda is m divided by L. That is our linear mass density for this thin rod. So we actually end up with here m divided by L times L cubed divided by 3. So now we're going to have some stuff cancel out here. So one of these L's is going to cancel out. That cubed is going to cancel out. So what we're going to end up with here for the rotational inertia, the moment of inertia around this end for a thin rod is we're going to end up with ml squared divided by 3. Okay, so just to kind of summarize what's going on here, again, we're still using this basic form for rotational inertia. We're still adding up all of those masses that are located at some distance, but that looks a little bit different for objects that have mass along its entire shape. Again, we're cutting it into these little bits and pieces here, and then we're adding those up along the entire length of this rod. That's why we had to integrate from 0 to L. That's why 0 to L are our bounds there, because we added up all these chunks along the entirety of this, the entire length of this rod. Now, again, with this linear mass density, you're always going to be given this if you're asked to do integration for a shape like this. Okay, and we're even going to do one in class where we actually have a volume mass density. That one gets a little bit more complicated, so we're going to kind of work through that one together in class. But again, you're always going to be given this linear mass density. And the key is that that is a constant value along this shape. That's why we were able to just plug in dm over dx, because that's the same, it's just a ratio between the mass and the length of that object. All right, well, this last slide here is just going to introduce us to what we call the parallel axis theorem. So what I have here is I have a hoop, and the axis of rotation for this hoop is running right through its center of mass. So it's running right through the center of that hoop. Now, the moment of inertia of a hoop about its center of mass is just mr squared, okay? It's just based on how far away this mass of the hoop is. How far the mass of the hoop is from, you know, the center, okay, from that axis of rotation. Now, let's say that instead of looking at the axis of rotation running through the center of mass, what if that axis of rotation was out here somewhere, okay, at some, we'll call it some distance d away from that axis running through the center of mass. Well, we can very quickly recalculate what the moment of inertia or the rotational inertia is here based on this new axis of rotation using the parallel axis theorem. So what the parallel axis theorem tells us is that this new rotational inertia is going to equal the moment of inertia based on the axis running through the center of mass, okay, plus the mass of that hoop times the distance that that axis actually shifted from the axis running through the center of mass. So what this new moment of inertia would look like then is it would equal mr squared plus md squared. Okay, pretty straightforward. So this right here, this is your parallel axis theorem, where we say that the new moment of inertia is the moment of inertia based on the axis running through the center of mass plus the mass of that object times the distance that that axis actually shifted from the axis running through the center of mass. So this slide's really short, just to quickly introduce you to the PAT, the parallel axis theorem. And we're going to apply this a little bit more in the coming days because I want us to really get more comfortable with actually calculating rotational inertia for various objects and based on various axes of rotation. So I hope this video lecture kind of cleared some things up. Hope it helps you understand rotational inertia a little bit more and where these funky equations actually come from. Okay, so take care, AP Physics students. We'll see you tomorrow. Make sure that you take note of any problems that you work on today that you might have trouble with, because we'll take a look at those tomorrow. All right, adios.